Hi everyone, hope you're having a great workshop. Sorry I couldn't be there. Many thanks to Lucas and Nadia for organizing such a splendid workshop, and hope you enjoy also the conference. So I will talk about some work that we have done and we continue to work on locally stable time-varying multi-seasonal ARMA models. So it's a time-varying model specifically about the seasonality. And this is a joint work with Ganna Fagerberg, who is my PhD student at Stockholm University, and also Robert Kohn, who I think is there listening. The structure of the talk is sort of the usual. I'm going to go through the model, the time-varying multi-seasonal AR model and ARMA model, and the parameter evolution in the time-varying scenario. And we'll explain how we do Bayesian inference and show you some simulation experiments and an application. So the slides are available from my webpage, including references, and the paper is on archive, and the ARMA extension will appear quite soon on archive. So the motivation for the work is starting out from Box-Jenkins ARIMA models, where you have to assume stationarity. Either just assume it, or you have to take differences in order to get a stationary process. And that's a global stationary, so it has to be the same parameters throughout time, and it has to be stationary. And that's quite restrictive. Often you have to take differences to get stationarity, and there's a potential information loss from over-differencing. The levels will be non-stationary, so if you care about the levels, they can be non-stationary, and it has been shown that you can get the poor short-run forecast from having to take these differences. So that's one way to get the globally stationary process to take differences. Another common approach is to just take data in the most recent regime. That's quite wasteful because you only get a limited share of the data that you have, and also the model then has no chance of actually giving some probability to a regime change if you restrict the data to just the most recent regime. So time-varying parameter models is a natural way to relax these restrictions, and it has a long history, of course, in statistics and econometrics, and also in signal processing. So more recently, there's been quite a bit of work on more realistic parameter evolutions. So the initial work with just homoscedastic Gaussian innovations has been replaced by sort of extensions of global local priors to time-varying processes like that. And we will use one of these innovations in our model here. The parameters can, if they're time-varying, can easily slip into explosive regions at certain points in time. And that's one particular thing that we want to avoid. So we will also look into the possibility of restricting the process to always be stable to avoid explosive behavior. So seasonality is something that is often removed before the analysis, and then you take the time variation on top of that. So we want to keep it. We want to keep the seasonality in the data and actually model it, because it's usually predictable, and so you want to model it jointly with the other parameters. The question then is it time varying? It could be. It depends on the application, of course. And we also want to tackle the case where you have multiple seasonal periods. So that's quite common nowadays. If you have data, say every hour, you might have a daily cycle, you might have a weekly cycle, and a yearly cycle, not just a single seasonal. So that's the multi-seasonal, multiple seasonal periods. So the regular seasonal AR, just to fix some notation, when you have P, little p regular lags and capital P seasonal lags, and you have a seasonality of season S, for example 12 if you have monthly data maybe. the standard AR model would then multiply a polynomial for the regular lag and a polynomial for the seasonal lag, for multiplied on the time series, and then potentially there's a mean also here, and the usual Gaussian IID errors. So L here is the lag operator as usual, and we have a regular polynomial, little phi, and then a seasonal polynomial, capital phi. And if you have multiple seasonal periods, you can just extend that. So imagine that you have a daily, weekly, and a yearly, so you would have 3 different seasonalities. You would just multiply additional polynomials like this. So we can extend the usual seasonal AR model to a multi-seasonal by just having more polynomials multiplied, 1 for each seasonality. So we want to enforce stability so we don't get explosive behavior at any point in time. And the way to do that usually is to have some set of unrestricted parameters. In this case, imagine that there's an AR2 model with just 2 lags. So you have 2 parameters unrestricted that you then want to map into the stationary region or the stable region, which in the AR2 case is well known to be this triangle. So we will get this map from the unrestricted via the partial autocorrelations and then over to the stationary region. So it's like 2 maps that you need in order to get from the unrestricted to the stable parameters. The first mapping from the unrestricted to the partials, there are many different ways you can do that. We follow Monahan, who originally did this. We have this parameterization, so from the unrestricted lag, kth lag, to the kth partial autocorrelation. And then from the partial autocorrelations to the stationary regions, well-known recursion that you can use to get the mapping from the autocorrelation, partial autocorrelations to the stationary region. So this map is going to be important for us, and we will use it on every polynomial factor, so ensuring that the whole model is stable. And the same mapping can be used on the MA coefficients to get invertibility. So we can enforce both stability in the AR part and invertibility in the MA part. So these unrestricted parameters have really no interpretation. They're sort of technical devices that depend on which particular mapping you choose there. So it's not obvious how to put priors on this. So what we do is we try to get as a baseline a uniform distribution over the stability region, so a uniform distribution over this triangle in the AR2 case. And we show using results from Jones that if the kth parameter, so the kth unrestricted parameter for the kth lag, follows a t distribution or a skew t distribution, depending on if k is odd or even. If you do that and they're independent, you actually get a uniform distribution over the stability region. And that can be extended to any number of lags. So later on we're going to use an extended Kalman filter, so then we would need the prior for the initial parameters at time 0 to follow a normal distribution in order to be able to use that. So we find the closest normal approximation to this that still gives a fairly uniform distribution. So this is what we're going to use at time 0, and then over time there's going to be another type of shrinkage process. So the time varying multi-seasonal AR model is then again this product of m different polynomials, but now the parameters are indexed by t. So they can all change the parameters. So phi t contains all of the parameters in the different polynomials. And then the map G is this mapping that I showed before from the unrestricted parameters via the partials to the AR coefficients. So this map G is going to be important for us, mapping the unrestricted to the stable parameters. In terms of the parameter evolution over time, we're going to use the dynamic shrinkage process from Dan Kowal and co-authors. for our time-varying seasonal autoregression model. So on the top here we have the transformation from the unrestricted to the stable AR parameters, and then we have the evolution on the unrestricted parameters. So the unrestricted parameters, the kth lag, follows a random walk with innovations, new kt for the kth parameter, which follow are independent Gaussian but with a time-varying variance. So the variance here is the exponential of some ht process, and this is the log volatility. And that log volatility itself follows an AR1 process with innovations that are following a Z distribution, which is a heavy tail distribution. And this construction makes sort of, it's a global local construction, so you're going to have a log volatility. So the innovations, the parameters here are going to change with different speed, different variances. And it will be a global variance factor, which on the log scale is mu k. And then it's going to be local variances on the log scale given by eta k following this heavy tail distribution. So you can imagine having a global volatility which is low, which allows the parameters to stay constant for long spells. And then all of a sudden you get one of these heavy-tailed eras that increases the variance, and you get a much more rapid movement or even a jump in the parameters. And that is going to be persistent because this kappa k is going to be the persistence parameter. So in the special case where this kappa is 0, this can be shown to exactly correspond to the horseshoe prior, where mu plays the role of a global on the log scale variance, and eta k plays the role of the local variance on the log scale. So the important thing is that this allows us for constant periods of parameters and then rapid change or even jumps in the parameters. Here's the simulation from the prior, where we can see on the middle part here, over time, we can see the evolution of the sort of total standard deviation of the parameters, which for the second parameter, the yellow one, shoots up a little bit here, and then we can see the phi's then sort of jump, and then there could be rapid movements and so on. So here we see that the end result, once we transform to the stable parameters, the phi, they can stay constant for long spells, they can jump, and they can move rapidly at other times. And down here we see the simulated time series from these parameters. So this multi-seasonal time-varying AR model, seasonal AR model, can be written as a regression with non-linear restrictions. So if we multiply out all the polynomials, for example, if we take the simple case where you just have one regular lag and one seasonal lag, if you multiply through this, you're going to get that you can write this as a regression on the lags, and the lags are going to be at t minus 1, t minus s, where s is the season, and t minus 1 plus s. So you get a regression type of model on the lags and specific lags depending on your regular and seasonal setup. What's important is that this becomes a non-linear regression in terms of the parameters, because the parameters, the three parameters on these lags are going to be little phi, big phi, and then the product, the orange part here, of the regular and the seasonal. And this is going to be, of course, much more elaborate when you have more lags, but we can always write it like this as a regression model with non-linear parameters. Should also note that there's a bunch of lags in between that have zero coefficients, and we'll use that later on also. So if you put it all together, the top equation describes the evolution of the time series. We write it as a non-linear regression, like I did on the previous slide, where the stable AR parameters are obtained from the mapping of the unrestricted parameters. So we have the unrestricted parameters mapped to the stable ones, and then non-linearly applied in this regression framework. And the parameters, I've written them all as vectors here. The parameters evolve independently, and they have this dynamic shrinkage process that I explained before. So the aim now is for Bayesian inference is to get the joint posterior distribution of the evolution of all the AR parameters, or the unrestricted or stable. You can always map it over, of course. All of the log volatilities over time. So 1:t means the whole time sequence of log volatilities. The global variance parameters, the persistence there, and potentially also if you have stochastic volatility in the measurement errors, maybe you want the posterior for that too, given the data from 1 to t, capital T. So previous papers have used, like Koala and his authors, co-authors, use Gibbs sampling, where they use the two sort of usual data augmentation tricks, rewriting volatility models by taking the square and the log, so and then expressing the log chi-square 1 as a mixture of normals. And then polygamma augmentation of the Z distribution, turning it into a conditionally Gaussian distribution. So after the augmentation, the transition model is going to be linear and Gaussian. So if you want to sample from the Gibbs sample from these different steps, all of the other parameters except the thetas are given in Kowal's paper, for example. So when it comes to the sampling of the thetas, the unrestricted AR parameters, we can note that it's a state space model with the state vector being these unrestricted parameters. It has a non-linear Gaussian observation model. As I showed, you can rewrite the seasonal model into a non-linear regression. And with the augmentation stuff, it's a linear heteroscedastic Gaussian state transition. So we started to experiment with particle Gibbs with ancestor sampling, which is a nice algorithm that is simulation consistent. It's rather slow, like many of these particle methods, if you use many particles. But the main drawback for us is that the dynamic shrinkage process, all of these global local evolutions, they imply near degeneracy in the state transition equation. Exactly what we wanted the parameters to be able to stand basically still for long spells of time. When that happens, you have near degenerate transition, and that causes problem with the particle degeneracy. So we instead tried forward filtering backward sampling based on the extended Gamma filter, because we have a nonlinear measurement equation. And that turned out to work quite well for this model. It's fast and it's also robust to the near degeneracy. It is approximate, but it's very accurate actually for this model. And also automatic differentiation makes it all quite beautiful and tractable, because the mapping that we have, the nonlinearities that we have, are based on two different things. First of all, this stability restriction. So we have this recursion going from the unrestricted parameters to the stable parameters, and then we also have this multiplying out of the seasonal of the polynomials. But all of that just works beautifully with automatic differentiation, because you need the gradient for this algorithm. So basically what we have is a state space model. After augmentation, it becomes a linear Gaussian, heteroscedastic Gaussian transition. These are controls, which we don't really have, but you could have. And then you have the measurement equation, which is this nonlinear function of the state. And to the left, you have Julia code for the standard Kalman filter, and to the right, you have the Julia code for extended Kalman filter. And you can see that the only difference is that if it was a linear Gaussian measurement equation, the C would just be a matrix, and then you can do the standard Kalman filter. With the extended Kalman filter, that C matrix is instead given by the gradient at the prior propagated step. Otherwise it's exactly the same. So here are some simulation results. This is the yellow lines show you the true evolution of the parameters. So we made up a certain evolution and then see if we can recreate it. And this is actually a model with 2 regular lags and 2 seasonal lags, but I'm only showing you the first 2 regular and the first seasonal to be able to fit on the slide well. There's the single seasonality here, so like 12, you can think about monthly data. And again, the yellow line is the true evolution, which, for example, the second AR parameter is just constant here, and then the first seasonal is constant and then jumps. The red lines, because it's actually 5 of them, show you the posterior median based on 5 different initial values where we draw from the prior. So this is sort of checking the stability of the algorithm across different independent runs, drawing drawing from the prior. And there's also 5 blue bands, which is also hard to see because they're on top of each other here, showing you 95 credible bands. So for the top row, we have the forward filtering, backward sampling X, meaning the extended Kalman filter. So that's sort of a preferred algorithm for us. You can see it's quite stable across the different runs. With particle Gibbs, with ancestor sampling, we have this row is with 10 particles, this is with 50 particles, and this is with 100 particles. And you can see it's much less stable. So this is caused by this near degeneracy problem, the fact that the parameters stand still, and that causes problem for many particle methods. So you need 100 particles, and still it's much less stable than the forward filtering, backward sampling with extended Kalman filter, which is of course much quicker than the particle methods here. So you could add a bigger offset to improve convergence of the particle filters. So for example, in volatility models, it's quite common to square and log and then add an offset. And that offset, if you make it large here, you can actually make particle filters work much better. So here we can see an offset which is very small. This is the machine epsilon in Julia. And there we see the update rate, which measures how often parameters change in the particle filter. And you have time here. So you can see as we go back in time, the degeneracy starts to hit us. We don't update much anymore. And towards the end, we don't update at all, basically. That's with a very small offset. If you use the offset in the DSP package by Dan Kowal, which is a bigger offset and is sort of adaptive, it becomes a little bit better, but still problematic. You still have very low update rates early on. If you shoot up the offset to 10 to the minus 6, it improves. So now with 100 particles, the update rate is reasonable. It's like 0.25 at least. But with that offset, you don't get any more the benefit of this global local shrinkage. So here you can see the first column, all 4 parameters now also including the second seasonal lag. With the machine epsilon, you get this sort of behavior that you would like, constant when it's constant and so on. With the DSP, it's a sort of middle ground. Now it's a bit more wiggly. If you shoot up to the offset to 10 to the minus 6, which is still not huge, but pretty large in the scale, we are tracking the data, but it's much more wiggly now. So this is the drawback of the particle methods. In order to make them work and not be degenerate, you have to push up the offset, and then you lose the benefit of dynamic shrinkage process. So some simulation results, a little bit quick, and then I go to the application. So we will compare this model and the estimation method that I mentioned with some benchmark models. These benchmark models are linear measurement equations, so we cannot directly compare parameters. I'll show you how we try to make them as similar as possible to our model. And also we want to compare with the models that non-parametrically or semi-parametrically estimate the spectral density. So we will not look at the performance of the individual parameters, but we will see how well the models can estimate a time-varying spectral density. And the spectral density for seasonal processes, here we can see from an AR1, seasonal AR1, they have these peaks at the fundamental seasonal frequency, and then you have additional peaks at every harmonic. So that is what they tend to look like. They have these multiple peaks. And the benchmark models that we compare with are listed down here. So it's AdaptSpec, for example, which is estimating time-varying spectral densities non-parametrically. So it doesn't really try to, it's not specifically for seasonal data, but you could potentially use it. And then we have TVReg, which is a package that does kernel smoothing sort of over time here. ShrinkTVP is a package for an alternative global local one, and we use the static version. So we're in the revision process, we will add their dynamic versions, which will perform better, I think. But for the moment, this is what we have. And then the DSP is just Dan Kowal's without the stability and without the seasonality restrictions imposed. So what I mean by that last part is that all of these models that we fit, the benchmark models except AdaptSpec, they are linear models, so they cannot really handle this multiplication of polynomials. So what we will do is to fit linear models with these seasonal lags. So this ZT will contain the first lag, the lag S, and then lag S plus 1. And we will impose the zero restrictions to make these benchmark models more closer to our models. So they will know where the zeros are in the polynomials in these coefficients, but they will not be able to handle the multiplicative restriction. They will estimate the parameters freely. So that's as close as we can come to these linear methods. We will look at the performance with respect to the time-varying spectral density or the instantaneous spectral density. So that's across the frequencies and time. And our measure will be the mean square error of the log spectrogram estimate. So we will sort of integrate the MSE, the squared errors over both frequency and time to get one single measure for how well you capture the log spectrogram. And down here we have box plots showing you, for example, that AdaptSpec struggles a bit here because it's not made for specifically for seasonal data. The DSP package does fairly well with this just linear, there's no multiplicative structure there. And ShrinkTVP does fairly well and so on, but the best one is our model with either FFBS or the PGAS. Both do similar performance. FFBS does a little bit better. And then TVReg is a little bit more up here. So this is the result in terms of the plot of the spectrogram. So we have frequency and time, and this is the true spectrogram, the one we're trying to capture. It's the same plot in this, in every plot here with the true, but if you go down to the second row here, that is the time-varying seasonal autoregression. And then the columns named 10% is the sort of 10% worse in terms of the MSE. So this shows you the behavior of the TV time-varying our model here when the model doesn't perform so well, but it still does pretty well here, right? And this is the median performance, and this is the sort of one of the better performance across all these 100 data sets. So we generate 100 data sets and then try to estimate the spectrogram. So regardless of, it's fairly stable behavior, even when it does poorly, it's similar to when it does very well. And then you have DSP, adapt spec, and the other methods, and you can see that they are a bit more uncertain about things, more wiggly and so on. And adapt spec, you can see that it struggles to fit this because of the seasonality. Here are some just snapshots in time. So at time equal to 100 and time equal to 400. This is the fit of our model for the true spectral density at time 100 is the black one behind here. And then you can see the 10% worst median, and then the 90% sort of one of the better fits. And they're all rather similar and capture quite well the underlying seasonal spectral density. Here is the DSP and the adapt spec. We can see struggles as we have seen before. And this is for TV reg and shrink TVP, so which is a little bit off in certain places. Again, the shrink TVP, there is a dynamic version that we will add in the revision, and it will probably do better. This shows you another picture of the same thing, but now we are fixing the frequency at pi divided by 4, and pi divided by 2. And we look at the fit over time. So now it's time down here. And we can see that our model captures this quite well. There's some deviations, of course, and other methods are not performing as well here. It's a little bit wiggly. TV reg sort of wiggly and also over smooths, and to some extent shrink TVP is also the same. Too much wiggle and also a little bit of over smoothing. So finally I want to show an application, and this is for US industrial production. It's more than a century of data. It's monthly data, so we have one seasonal frequency, which is 12. And here's the data plotted as the raw series, where we have the training data, and then we have some test data, which is the yellow one, which is what we use to determine the lag order. So we use log predictive scores out of sample to determine how many regular lags and how many seasonal lags. We detrend this because we want to focus on the seasonality and also the variability. So we keep the variability and also the seasonality. And this is the actual data that we will fit the models to. And we also take log before that. And then we fit the SAR 1, 2, so one regular lag and 2 seasonal lags, using this forward filtering backward sampling with extended Kalman filter with 3 different initial values, so random initial values to show the stability. Here we see the regular lag is not varying much over time. So here's the posterior median in red, and then you have 95% credible bands. So it's sort of a downward trend of the regular, but it's not big changes, even though it's more than a century of data. The big changes are in the seasonality. So during the Great Depression and the Second World War, the first seasonal coefficient and the second seasonal coefficient becomes quite different. And actually the seasonality during these periods are basically wiped out. So it's very close to 0, and this is also fairly close to 0. So we can clearly see big jumps and then constant behavior in between. So a long period of constant seasonality until COVID hits, and then again we can see that the seasonality is not quite wiped out, but it becomes a different pattern. And here is an illustration of the spectral density, how it changes over time. So this is from the same model that we fitted, and this shows you over the years how the spectral density has changed. So if you go in the beginning, the 1920s and so on, it has this behavior, and then as you approach the Great Depression, you can see that things become quite different, and now a lot of seasonality is sort of wiped out here. This is plotted on the log scale. If you plot it on the original scale, you see even more that there are no bumps anymore at the seasonal frequencies. So during, again, back to the log scale, during the Great Depression and the Second World War, the seasonality is sort of wiped out almost. And then after that, we get back to the previous pattern with a pretty strong seasonality until we get to COVID, where we still have seasonality, but it changes pattern. So you could see there in the COVID years that it becomes this second bump here sort of goes away. If you instead would have fit a static model, it would concentrate on this long constant period. So if I click here, I can see the yellow line being the log spectral density of the static model. And it's very similar during the period in between. This is 1966. But if you go back then, because it's a static model, it doesn't change over time. It does a terrible fit during the Second World War and the Depression. It's even worse if you look on the original scale, where the red one is the time-varying model at 1943. The yellow one is the static, which, again, it focuses on this long period and then completely misses the other periods. So, finally to conclusions. We developed a multi-seasonal AR model with time-varying parameters. We have extended that. I didn't show you that, but we have extended it to MA, and where we also sampled the epsilons and so on as a separate Gibbs updating step. Otherwise, it's very similar. We have stability restrictions at every time point, so that's sort of locally stable. And the parameter evolution is given by this dynamic shrinkage process, which allows constant periods, jumps, and rapidly changing parameters. This gives a challenge in the inference problem because it's a non-linear, both because of the stability restrictions and because of the multiplicative seasonality. And the dynamic shrinkage prior promotes near degeneracy, which gives problem with particle filters. So we both tried particle Gibbs and extended Kalman filter. Extended Kalman filter is faster and tends to work better, is more robust. But there are situations where the Kalman extended Kalman filter may struggle, and we are already working on going beyond the extended Kalman filter to more elaborate sort of extensions of the Kalman filters with better approximation properties. The posterior sampling for the DSP prior, I think we could improve on that. It's rather sticky and not so efficient. So that is a separate work, and also to get better priors, because it's pretty hard to estimate these parameters lower down the hierarchy, like the global variance and so on. So if you can define better priors, that could be helpful also for getting better results. We are working or completing a Julia package where we can estimate an arbitrary number of polynomials, all handled by polynomials and automatic differentiation. So that's what I wanted to say. Thank you, and I hope you enjoy the rest of the workshop and conference.